My name is Joshua Reuter, and this is my creative assignment for Deformable Bodies, COE 3001. Today, we will be talking about torsional mechanics of wind turbine shafts. When designing a wind turbine, there's a couple engineering challenges that come along with it. Wind turbines need to convert aerodynamic power, or wind, into torque. The shafts transmit torque from the rotor to a generator via some coils, and failures could mean costly downtime in renewable energy systems. So it's very important that these machines are both efficient and economically probable to install and manufacture. A lot of times when we see wind turbines, we see them with three blades. Each blade is shaped like an airplane wing in order to generate a lift force. That lift force, cross product with the position of where that force is at, is generating a torque. The equation for torque is the force crossed with the position vector, and anytime you have a torque centered around an axis of rotation, it will create the desire for the rotor to turn, or that axis to turn and rotate. And in a wind turbine, when that rotor turns, it turns inside of a coil which generates electric power, which is why they're used to turn wind energy into electric energy. Occurs, it is resisted by a shear stress. Shear stress is given by the torque times the radius of the rotational member divided by the rotational inertia of that member. Shear stress increases as the radius increases. Therefore, the further out you are from the center axis of rotation, the higher stress occurs. That means if a force is applied on the furthest outside surface, it affects the torque and the shear stress more than if that exact force were applied closer to the center axis of rotation. Shafts are often designed to be hollow for peak efficiency and shear stress maximum. We'll come back to that later for our example problem at the end of this lecture. As I said before, the distribution of the stress is directly proportional to the radius or the distance from the center axis of rotation throughout the cylindrical material. The geometry of the cross-section of the material determines the moment of inertia in the shaft. Since we're working with a solid circular rotor, we use the solid shaft equation for J, given on the top line of the slide, where pi times r to the fourth power divided by 2. That is our moment of inertia. For a hollow shaft, it's the difference from the outside diameter to the inside diameter over 2. And as I hinted at earlier, larger diameters increase J significantly, especially since they're to the power of 4 in both of these equations. Hollow shafts save weight while maintaining the max stress, and even sometimes more max stress, because as we can see, the vectors just shown on this picture on the right are a lot smaller. So there's almost a waste of space in the center of this cylindrical shaft. Up this lecture and compare the difference between a solid shaft and a hollow annular shaft. I generated 2 example problems so we can compare the max stress outputs of each. As you can see, I wrote some code to help with the calculations. And in this case, a mid-sized wind turbine transmits torque from its rotor to its generator through a solid steel shaft. At a particular wind condition, the rotors produce a torque of 5 times 10 to the 5 newtons, and the shaft between the hub and the first support is 6 meters. The shaft has a radius of 0.3 meters. In order to calculate this, we take the torque and multiply it by the radius, and then we divide it by pi over 2 times the radius to the 4th power. This gives us 11.789 megapascals. We do the exact same problem, but we give the shaft a hollow core with an inner radius of 0.25 meters, and we do the exact same calculations with the new adjusted moment of inertia from previously in the slides. We can see that we reach 22.77 megapascals, which is almost twice as much shear stress, with the majority of the shaft being hollow. Comparing the two results, we see that a hollow annular shaft is more efficient in terms of material than a solid shaft. Thank you for your time.